Thank you. This is joint work with Red Valiant. We focus on the age-old problem of predicting the future in this work, and there has been a huge body of work on this topic. A popular approach to this problem is to cast it as an online learning problem, where the predictor has access to a group of experts. On each day, the predictor will make a prediction based on the expert's advice, and then he observes the true outcome on that day so that he can re-evaluate the experts. At the end of the day, we compare the performance of the predictor to the performance of the best expert from hindsight. And it is well known that in many different settings, this average performance can be arbitrarily close to the performance of the best expert. And also this guarantee holds for any data sequence that can be chosen adversarially against the predictor. So if we summarize this into a table, we know that online learning makes no assumption on the data distribution, but it does require a group of experts to make the result meaningful. An alternative approach does the opposite by making strong assumptions on the data sequence. Say the sequence comes from a hidden motif model with a few states, and under these strong assumptions, we can prove results that are independent of the experts. And the motivation of this work is to get the best of both worlds by not making any assumption on the data distribution or using any experts. And the key observation here is that most previous work requires a predictor to make a prediction at every single time step, and we are going to relax this assumption by allowing the predictor to be more selective. More formally, we have the following model of selective prediction. Suppose we have an unknown data sequence of length n. Each data point xt comes from a space 3x. And this prediction task also comes with a family of statistics where each function simply maps a few data points to a real number. And the prediction will proceed as follows. At any time step t, after we have seen the first t entries in the data sequence, we can make a prediction by choosing a number m between 1 and n minus t and predict the function value of the next m numbers. And importantly, we only made one prediction along the time horizon, and it is selective in the sense that we can choose when we make the prediction as well as the length of the prediction window t, length of the prediction window m. And the goal is to minimize the loss in our prediction, which is a function based on the gap between our prediction and the correct answer. It is also worth pointing out that in this model, we allow the data to be quite arbitrary, but it cannot depend on our actual prediction, so that the adversary is kind of arbitrary but non-adaptive or oblivious. And as a very special case, if the data sequence is just a bounded number sequence, and the function is just the arithmetic mean, we get what we call mean estimation problem, where after we have seen the first t numbers in a sequence, we try to choose the window length m and predict the average of next m numbers. And it turns out that for this case, there's a very simple algorithm that achieves a non-trivial loss, which is simply by choosing a window length m uniformly at random from powers of 2, and then we pick a random stopping time t from multiples of 2m. What we will do is to ignore the first t numbers in that sequence. We compute the average of next m numbers, and we claim that the next m numbers have the same average. This algorithm can be best visualized as a binary tree, where we view the sequence as leaves of a binary tree, and we are going to pick a random level uniformly, and also pick a node in that level uniformly at random. What we do is to compute the function value, or arithmetic mean in this case, of the left subtree, and claim that the right subtree has the same function value. Given this recursive nature of the algorithm, we can analyze it quite easily, and turns out that it achieves a squared error of 1 over log n, or absolute error of 1 over square root log n on any data sequence. And this result was first obtained, but stated in quite different terms by Andrew Drucker in 2013. We also prove a matching lower bound for this problem by constructing a distribution over hard instances that shows that this 1 over log n rate is optimal. We also extend all these results to more general functions beyond the arithmetic mean, including what we call smooth functions and concatenation-concave functions, and we will focus on this latter one in this talk. The motivation for this class is what we call the learnability problem, where here we are going to view each data point xt as a label example, say an image from ImageNet and also a label. And what we want to do is to predict the following. Say if we are going to fit the next 10,000 images using a linear model, what is the minimum loss that we can get? So more generally, suppose we have a concept class group L, And we define the learnability with respect to L as the minimum loss that we can get over all the concepts in script L. And it turns out that the key observation is as follows. We know that arithmetic mean is kind of concatenation linear in the sense that if we concatenate two sequences together, the average of the new sequence is the average of the two means. And for learnability, by definition, this new learnability is lower bounded by the average of the two learnabilities. And thanks to this property, it turns out that learnability, or more general, any bounded and concatenation-concave function can be predicted up to the same rate of 1 over log n in expectation. And let's go back to the learning problem that we consider. And we already know that no matter how complex this script L is, we can predict the learnability of unseen data arbitrarily well. The natural question is that, can we actually find a specific model in that class that actually fits the next data points well? And more formally, we can extend our setting to the learning setting, where at some time t, the predictor should output a window length m and also a model from that class, such that the excess risk is small. Here, the excess risk is just the difference between the average loss and the minimum loss that can be achieved. It turns out that a very natural attempt is to sample the two intervals as before, and we try to minimize the empirical loss over this training set A, and hope that it will behave well on this testing set B. And it turns out that we can, by a very standard argument, we can prove an upper bound on the excess risk that scales polynomially in the size of a script L. But in classical learning theory, strong results often scale polylogarithmically in the size of L, because that's an upper bound on the VC dimension or any other complexity measures. But it turns out that this bound is already tight for the ERM algorithm, so that improving this basis rate will require more sophisticated algorithms. So in this talk, we have seen that by allowing the predictor to be selective, we can make some seemingly impossible tasks to be doable, and this is without making any assumption on the distribution or the experts. And it remains an open area of research whether this selectivity brings more power in many other natural prediction settings. That's all, thank you. Say that instead of the sequential setting, we can imagine that the predictor can explore the sequence or the data like arbitrarily. Another thing is that suppose we also have a group of experts, and can we do, say, the minimum of the expert problem and also like this this selective setting? Yeah, I guess the motivation of this word is like applications where it is enough to be like accurate about some proportion of the sequence, so that we can like leverage this selectivity.
Can you say a few words about the proof techniques?
Oh, sure. The proof, for the mean estimation, like the proof really builds on a potential function argument where we define a potential for a sequence of average mu. And what we show is that when we decompose the sequence into two halves, like the decrease in this potential can compensate for the loss between these two halves, so that we can bound the